So when we talk about boundary conditions for beams in bending, we discussed in class that if you have a beam with something in the middle, like a spring or a support, then you have to break this here um, in two parts. And the reason for that is when we actually took an incremental element and applied the Taylor series expansion on this element, saying that my shear force is V here and V plus dou V over dou x 1. Now you cannot expand the Taylor series expansion across this spring. So that's the reason we break it. And Professor Rosini covered in class that the first part should be this, then there will be a small section, the incremental section which is connected to the spring, and then there will be another part at the end. So you have to divide this beam in this way, and you can write the shear forces and moments at this infinitesimal part, but the final boundary conditions would be two boundary conditions here for a beam in bending, two boundary conditions here, two boundary conditions here, and two boundary conditions here. So you'd have to connect the values which are present on the right end of this beam to the left end of that infinitesimal section.
Okay, so basically, like if you had a spring, so you'd have that force going up, going downwards off of the spring, and then so your sheet, like if you did it on the left side, it would be V2 up, and then it would be FK, like FSK plus V plus V2 plus dV over x1. That's how you would do it?
So you would have to write all the forces on this end and then on this end.
Yeah.
And the spring force, and you will apply equilibrium and moment balance on this body itself.
Yeah.
And then you have one value here which is V, which would be equal to this equal and opposite.
Yeah. Okay, so like, but we still, like V2 would still be a variable in that equation, right? So like you'd have V2 on one side, V2 plus Fs plus dvx1 over x2 on the other side. Is that true or no?
So you would have a variable, yes, which is V2 of say first part,
Yeah.
and then you would have a V2 of the second part, which is here, and then you have to eliminate V2 of 2 basically. So you'll solve these equations for balance of forces and moments.
Okay.
And then you will say that my this value is equal and opposite to this value, so you have the shear force boundary condition there, and then you write that H 33 d cube u over dx1 is equal to this value which you calculated from the infinitesimal portion.
Yeah, I guess what I'm wondering is like that V2, how do we get V2?
You have to do the balance of forces and moments here, because this independently should be in equilibrium.
Yeah.
So you have two forces, a moment, the spring force, so you balance that, and then you apply moment at one end, and balance the moments of everything.
Okay.
Yeah. Try it out.
Yeah, I know how to do it, and I think I know how to do it, but I'm just not sure if it's like right, because my equilibrium equation would just be like negative V22 plus FKS that, and then plus V2 plus, and then plus V2 plus dV dx.
Yeah.
So that's my equilibrium equation, and then I'm solving for V22, basically.
I don't think you need to have the derivative dv over dx there, because of the same reason that we cannot have the Taylor series expansion. You just have to have a v2 of 2 in positive upward direction on the right end.
Okay. Can you maybe write out the equation of equilibrium?
We can go over through that in the office hours. I don't want to do it in class.
Okay.
So yeah.
Okay.
Because I'm interested in knowing how you do too, so.
Yeah. So again, I would say office hours, because there are distance learning students too, and I think we should go on with the class as as soon as possible.
Today is at 3, right?
Yes. Yeah. Okay, so far a lot of torsion has been covered. Torsion for circular sections, then elliptical sections, and then rectangular sections. So this is a short exercise which I have come up with, and what it does is it essentially has a circular cross section which is solid, and we are finding what is the diameter of that minimum diameter of the solid cross section that we need, so that we can take care of the shear stresses which are coming onto the beam. So the problem starts with an allowable stress which is given 300 megapascal. So a lot of students had this question of how do we get shear stress if we are given allowable stress. So if you look at the Tresca criterion, you can just divide it by 2 and get the allowable shear stress. So simple formula where the tau is equal to half of sigma 1 minus sigma 3 if sigma 1 and sigma 3 are your principal stresses, but you don't have principal stresses here, you have maximum allowable stress. So you just replace sigma 1 with maximum allowable stress and you get it. So that we use here to get the shear stress which is allowable, and then moments are given. It's 2 kilonewton meter, and sigma A is 300, which is already given. So let me just maybe, yeah. So standard formula for torsional stiffness of a beam which is circular in cross section, and then what we are doing is we are using our equation for calculating what should be the radius here, right? So we will get some solutions. Some are complex numbers, so we just discard them. We take the real value which is positive, and then we multiply it by 2 to get the diameter which is minimum. So in this case it's 0.04 meters, which is required to take that load which was initially in the problem. But that's not the main concern. The main concern is to reduce the weight of this beam, and we will do it by taking a hollow beam. So so now if we have a hollow beam, for a hollow beam the torsional stiffness is with this expression where we have an internal diameter and then internal diameter and outer diameter for the shaft, and we calculate the internal diameter in terms of the outer diameter. So when we solve this equation, we get multiple solutions which are complex, some of them are real, and then we have to pick out the positive root as before. So we get an expression of internal diameter which should be if you fix an outer diameter for the shaft. So by doing this, we can actually plot what internal diameter should be when you are changing or when you are picking a particular outer diameter for this kind of load, and when you increase it, the internal diameter also increases, but you see a jump in the internal diameter here, right, in this region. So what happens is if you increase the outer diameter by a little bit, for example, if your initial outer diameter was here and then you go to the outer diameter by just this increment, your internal diameter will increase from almost 0 to this portion, right? So you take out this material, essentially it weighs less, significantly less. So when we compare the weights, we see that a slight change, for example a 10% increase in the outer diameter, will actually reduce the weight by almost 30%. So that's why we try to design hollow beams, hollow shafts for beams in torsion, because the central portion of the beam is literally taking very less stresses, very less shear stress, because the variation of shear stress in the cross section is linear, and it linearly increases till you reach the boundary. Right. So this is just a short exercise which I just wanted to share with you.
Sorry, so about the torsional stiffness,
Mm-hmm.
which units are they used? I use over there because in one of the exercises we had kind of a weird unit that do not match with this one here.
Mm-hmm. For torsional stiffness?
Yep.
Let's see.
Should be torque per angle, right?
Yeah, an angle doesn't have a unit. So torque?
Newton meters.
Yeah.
Pascal is Newton over m squared. R to the fourth.
Yeah.
Divide that, so it's Newton per meters. That
So
would be original stiffness.
let's see.
Over divided by radian.
Mhm.
Yeah.
Yeah.
Newton times meter squared.
So it will be Newton times meter square.
Yeah, okay, and that's where we agreed. But for instance, in problem 5 at point 4,
Uh-huh.
it's, I mean, maybe I'm wrong with the conversion of KIP dot feet,
No. So
but it, you divide by like,
It is
yeah, but it's still
kilopounds
like
times foot squared.
Newton over square.
Yeah, so we can discuss about the problems in the office hours or later after class. The main thing is that the units in that, those problems are not in SI units. So I think they are in foot-pound second
Yeah, I mean,
system.
that's
Yeah.
like I can convert numbers. That's
Yeah,
not
yeah,
the
yeah,
problem. The problem is the dimension at the end of the day, which is going to be Newton over square meters, and not Newtons per square meter. But okay.
Okay, yeah, we can look at it in afterwards. Okay, so now let's move on to the elliptical cross section which was discussed. Again, a short, quick exercise.
excuse me.
Yeah.
Can I ask a question about the yield criterion, like the axis system? So when the yield criterion in the textbook in chapter 2 is written in Cartesian coordinates,
Mm-hmm.
but in the homework, I know this is the homework, but if you're in polar coordinates, how does that translate? I know it would basically be alpha, r, and x1 would be like the 3D coordinate system. However, like if we have an m3 moment applied, how do we get m3 decomposed into alpha and r?
If you have an M3 moment applied, I would suggest solving the problem in Cartesian coordinates.
Okay, so then we have to find a tau 1,2 and a tau 1,3.
Mm-hmm. Yeah, and then you have to use that equivalent stress formula to
Yeah.
use tau 1,2 and tau 1,3.
Okay.
Yeah.
So, thank you.
Okay, so we have an elliptical cross section here with A as the horizontal dimension and B as the thickness or half of the thickness of the elliptical cross section. So we I think derived these solutions in class, and I will not go over through the solutions, but what I want to show is that you can plot the shear stress, and I want to show the shear stress variation when you move from a circular cross section to an elliptical cross section. So this is just aspect ratio which I'm increasing. So you can see that initially the shear stress is the same around the edges because it's a linear variation for circular cross section. For example, I'll take this cross section and it's a linear variation. So the circumference is at a same distance. So if you take a circle, the outermost points are at the same distance from the center, so the shear stress is the same, right? But in ellipse, it doesn't happen that way. So when you change the aspect ratio, when it becomes an ellipse, you can see that you get higher stresses on parallel to the edge or parallel to the width of the elliptical cross section, and then you have lower stresses in the in the regions where you are looking variation across the thickness. So similarly, when you calculate the warpings, again standard formulas, you increase the aspect ratio, you see that potato chip formation, where now, because it's not a symmetric cross section, or it is a symmetric cross section but it's not uniform circular cross section, so there is going to be warping out of plane. That's what we solved in class. So if it was a circular cross section, there is no warping out of plane. Even after deformation, it kind of remains flat, whereas when you take a elliptical section, there is going to be warping in and out of plane, and the anti-symmetric solutions, so positive, negative, positive, negative, so that causes a potato chip like formation. Okay, moving on to the other one. Now it's the torsion of rectangular cross section. So in class we did that you can represent a Prandtl stress function for rectangular cross section by using a double Fourier series summation. So it's the same thing here. We are evaluating the tau 1 2 and tau 1 3 using this function which we initially assumed, and then we are just using this relation to get the tau which is effective and the shear stress magnitude. So you can see when I plot the shear stress variation, so initially I took a square beam, and you can see that let's say this is my thickness and this is my width of the beam, and I initially would take a square beam and then would move to a thin rectangular beam. So when I have a square kind of beam, my variation through the thickness is a huge variation, and same as the variation along the width. So you can see it goes from 0, goes to almost 0.5 and then comes back to 0. But then when I increase the aspect ratio, means I'm just increasing the length as compared to the width of the beam, you see that this variation kind of dies out. And now if you move from one edge to the other edge, you almost have the same shear stress variation along the length. So even if you use a very good solution to solve a thick problem and you enforce the dimensions of a thin cross section, you kind of obtain that the shear stress variation is very negligible when you move along the width of the beam. And we will just make this assumption now, and we will capitalize on this assumption and make our equations simpler. That's what we are going to do in the present analysis. And similarly, I'm calculating warping using the solution which we chose earlier, and you can see that there is hardly there is some warping because it's not a circular cross section, but it's not significant. But when it comes to a thin cross section, the warping increases, and we receive a similar anti-symmetric solution as we showed for an elliptical cross section. So kind of like a potato chip formation in a new design. Okay, so let's move on. I'll use Professor Rossini's slides and some of my notes to go over through this rectangular cross section which is now thin. He kind of introduced this in the last class, but let's go over through that. So yeah. Yeah.
Did you post those files on the Common?
Not yet. I can do that today. Yeah. So as we saw in the animation there, that when we increase the thickness, or when we reduce the thickness of that section, then it becomes a thin wall section, and the variation of shear stress along the width becomes negligible. So let's first define our coordinate frame which is I3, I2, which is the through the thickness coordinate, and I3 is along the width. So we are saying that essentially our shear stress is not varying along I3. So dou phi over dou x3 square should be almost equal to 0, right? There is no variation. So what we are left with from the Poisson's equation, our Poisson's equation was right, and we are saying that this term almost goes to 0. So we are left with d square phi over dou x2 square is equal to minus 2g kappa 1, right? And now because we do not have dependence in two variables, we can just simply integrate this equation to get our solutions. So so we have integrated twice because this is a double derivative, and we get two constants c1 and c2, and we need to solve for those constants. So we need some boundary conditions, and the boundary conditions we have is that let's say if this is the thickness, then at x2 t by 2, at that location I don't have any stresses, right, because it's a free edge. So I will just say that I don't have any stresses at x2 plus minus t over 2, so that function goes to 0. So we will get c1 0 and c2 is equal to g kappa 1 t square over 4.
Excuse me?
Yeah.
Why is the d squared pi over dx3 squared term around 0 if the x2 variable is the one that's small?
So if x2 is small, we saw that that the variation in the shear stress is almost negligible along I3. So initially, I can switch back. So initially, the variation you saw along the length was significantly high, but when you make a thin-walled assumption, for example here, when it was a beam with aspect ratio 1, means both the dimensions are the same, then you have along the length a huge variation in shear stress. But when you increase this, when you decrease the thickness, then the variation in the shear stress is almost negligible along the width. Is that clear? Like what I'm trying to say is that when you move from this point to this point, or this edge to this edge, you see that everything is one single color along a particular axis of coordinate. So if you are moving towards the edge, then it's purple, purple, purple everywhere. If you're moving through the center, it's almost yellow. So there is hardly any variation along x3, and this variation along x3 is 0. So means the derivative is 0 because it's not changing. So now we have c1 and c2. We will substitute these values to obtain our function. So phi of x2 becomes minus g kappa 1 x2 square minus t square over 4. Okay, so we have to reach there. We have to evaluate the shear stresses in the cross section, right? So now I will calculate the resulting torque. I have the expression that my twisting moment is equal to 2 times integration over the area phi dA. So I will just substitute phi here in this expression. So integration over the area g kappa 1 x2 squared minus t squared over 4 dA. Right? Yeah. And then I will split dA now because I have a dimension which is, let's say, b and thickness t. I don't have any variation along I3. I do not have any x3 in this equation. So I can say that this becomes integration from minus t over 2 to t over 2 because I have the variation along the thickness in the shear stress. Remember, this is torsion, so there is variation along the thickness and it's a linear variation. And now I have x2 squared minus t squared over 4. I can, g and k are not variables in this integration, so I can bring them out, and I have b times dx2 because it's integration over the area, and I can just take b out of the integration. So what I'm left with is 1 by 3 g kappa 1 b times t cube, and this is the same result which was obtained after reducing the series solution. Okay, so now we will use our standard definitions for shear stress, and I had tau 1 2 is equal to dou phi over dou x3, which is 0 because this variation of function, the stress function along the width, is 0. So I'm setting this equal to the 0, and then I have tau 1 3, which is equal to minus dou phi over dou x2, and I have the function for phi, so it becomes 2 g kappa 1 x2 x 2 g kappa 1 x2, and it is equal to 6 m1 over b t cube x2. So now you can see that in our shear stress expression which we obtained, tau 1 3 is in a linear variation with x2. So if you increase, or if you go from minus t over 2 to t over 2, in the cross section, there is a linear variation similar to what you saw in the circular cross sections. So you can see that this is kind of a linear variation if you go from this coordinate, which is minus t over 2, to t over 2, and this variation is governed by this expression. So if you reduce the thickness or increase the thickness, that's going to have a huge effect on this value as compared to reducing the width of the cross section or increasing the width of the cross section, but because it's a single power. Okay, so now because the variation is linear, the maximum for the shear stress will be at the boundaries. So the tau max will be at plus minus t over 2, and let's say we are taking only the positive one. So when you substitute that in x2, you get 3m1 over bt squared. So that's your maximum stress which you can evaluate, and then based on that you can design your thin walled section. If you're given a particular allowable shear stress, you can use that expression to evaluate your shear stress which is coming in the section, and then you can make a decision whether that beam is good enough for your problem. And then we will solve for warping. So if you recall the warping functions, they are and for x3 you have right. So in our problem, d phi over dx3 is 0 because there is no variation along the width of the beam. So this becomes x3, and d phi over dx2 is already evaluated as 2g kappa 1 x2. So when you substitute here, the g kappa 1 terms go away and you're left with x2. So it will be 2x2 minus x2 goes to x2. Okay. So now we will solve for these warpings. So phi from this equation comes out to be x3 times x2 plus a function of x3. So from this equation I will get this solution, and then I will get another solution from the above equation. Right. So if I want to have a unique warping solution, what should be the value of these? If we want to have a unique warping solution for the section, what should be the value of these functions? 0, right? So that my warping solution finally becomes x2, x3. And we have a relation of obtaining the displacements if we calculate the warping solution from the preliminary definition of kinematics in torsion for a beam in torsion. right? So it is again an anti-symmetric solution. As you can see, it will be positive in the first quadrant and the negative. So if this is your section and this is your coordinate frame, then this will be positive in this quadrant because x2 and x3 will be positive. It will be negative here, it will be positive here and negative here. And these positive negative signs are associated with displacements out of plane. u1 is coming out. So when you have an anti-symmetric solution, you again get a warping like a potato chip. So this will come out, this section will come out, whereas these two quadrants will go in the plane or of the board. So you receive like a potato chip kind of section. So we are able to retrieve that our displacement solution is anti-symmetric. Okay, so now that we did a thin-walled rectangular section, it's important to identify that what can we do with sections which are made of different thin-walled sections. This is just a repetition of the assumptions. We made an assumption that the thickness is much smaller than B and the shear stresses are aligned along the larger dimension. They vary linearly, as we saw, through the thickness, and they both the stress functions are associated with shear stress distributions. So just a repetition of what we did. So we calculated this and the tau max, and so this is kind of the deformation pattern which you will see from this function. So the positive, initially the dotted section was the cross section, and then you can see a positive movement outwards in the first quadrant and the third one, and then a negative movement backwards. So this is how the section warps in case of a rectangular beam, rectangular cross section. And we calculated that. Here x1 just means that it's kappa 1 is a function of x1, that's all. There is no variable in this expression. Okay, so what do we do if we have multiple components in a same cross section? For example, we have this as a rectangular thin wall beam, and then we have a semicircular cross section, and then we have a rectangular thin walled section again. So in any case, we obtained an expression for the torsion stiffness of a thin walled beam, and that is H11 is equal to 1 over 3 GBT cube. So this is for a rectangular section, right? So if you have any thin walled section, you can just calculate the length of that beam. For example, I have a section like this, right? So this section has a particular thickness. We have a coordinate C, not a coordinate C, but definition of a curve C, and we say that our curve is at half the thickness of the thin wall beam, and it spans the entire width of the thin wall beam section. So we take that curve, we identify length of this curve, which we term as L, and that's what is being used here. So we take the length of the curve, and the length of the curve is identified by a coordinate S, which goes parallel to the curve. So first we identify that we have a thin walled section, it has a particular thickness, we find the curve which is in the middle of that thin walled section, so it goes at the middle thickness, the curve which is there, and then we calculate the length of the curve by a coordinate which moves along that curve. So this is the length for this section, and then the circumference of this semicircular section will be that the length of that portion, and then we have another length. So sometimes they are referred to as S1, S2, S3, and then you just calculate S as S1 plus S2 plus S3. So and that becomes your length of the curve. So if you use the same expression that we evaluated for a rectangular cross section for torsional stiffness, you just replace B, because in our case B was the length along the S coordinate. So if you take that length and you just replace B with that length, you should get a reasonable estimate of the torsional stiffness for any kind of cross section. And the variation, as we saw in the previous slide, so the variation is very minimal along the length coordinate of that curve. So there will be a variation in the normal plane. So whenever you see a thin walled section, you can just for example here, you can just make a normal line through the thickness, and there will be a linear variation in the shear stress in that component. And similarly for all the regions in the cross section. Okay, now for an arbitrary cross section, the only non-vanishing stress component is the tangential shear stress acting in the direction tangent to the curve C. So tangent to the curve, the shear stress variation is going to be minimal. That's what we have assumed so far in our thin wall discussion. And then at a distance of plus T over 2 or minus T over 2, which is these faces here and here, the magnitude of shear stress can be evaluated because there is a linear variation there. And the maximum shear stress can also be expressed in the same terms as we calculated for a rectangular section, which I erased. But we got the similar function expression, 3m1 over b3q square. Okay, now a more general thin walled beam, if you have, then what you can do is divide such kind of a beam in multiple parts, because you know that this is formed of a rectangular strip and then a semicircular strip and then a rectangular strip again. So you can just separate this complete thin walled section in 3 parts. You might have this part and then a semicircular part and then again a rectangular part, and you have expressions for torsional stiffness for all 3 of them individually. And as usual, as like the bending sectional stiffness, even the torsional stiffness are additive in nature, so you can just add them up as shown in this expression. So H11 is equal to sum of the H11 of individual components. So if we have 3 components, then you have the 3 summations there. And then you can use the same H11 to calculate the tau S max, which will be at T over 2 or minus T over 2, because it's a linear variation through the thickness. So some notes, thin walled open sections, shear stresses are linearly distributed through the thickness, and the torsional stiffness is proportional to the cube of thin walled thickness, right? So the thin walled open sections have very limited torque carrying capability, because if this thickness goes smaller and smaller, then this H11 decreases by a huge amount, right? Because it's cube of the thickness. So the thin walled open sections, they can warp out of plane. For example, this section over here. If you apply some torque on it, then according to our theory which we have formulated, something like this should happen. In this area, this should come out of plane, and in this area it should come out of plane, whereas in this sections it should go inside the plane. In open sections, it happens that this portion comes out of plane and this goes back in the plane, so it is warping. Whereas if you had probably a closed circular loop like this, it becomes a thin walled section, but it's closed, so there won't be any warping. So it becomes stronger in torsion. The torsional stiffness will be higher as compared to an open section. So if you see the aircraft wings, they are always a closed section to make them stronger in torsion. If they were open sections, they would just not work in torsion, right? The allowable stresses would be very low. Okay, so now we talk about a general thin walled beam which is not in torsion but in bending. So we talked about thick beams in bending through the Euler-Bernoulli beam theory, but we did not talk about thin walled beams if they are under flexural deformation. Okay. So I will just introduce this concept, and we will cover most of it in the next class. So in general loading conditions, we make these assumptions that the stress components acting in the plane of the cross section are assumed to be negligibly small as compared to other stress components. So now we have a thin walled beam, and we do not have torsion, we have a shear force, right? So if we have a thin walled beam and if we have a shear force applied in a particular direction, so we used to have a axial stress induced in the beam, right, with a linear variation through the height of the beam. For example, if we have a rectangular thick beam and we are applying a shear stress at some point, a shear force at some point, so the variation in the axial stress would be something like this, right? A linear variation. So we do not now we don't have any torsion in this beam, so the variation along the thickness, which was linear, is not there, because that was for that loading condition when we were applying a torque at the cross section. So we say that the stresses tau 2,3 and tau tau 2,3 is significantly small as compared to tau 1,2 and 1,3, because there is hardly any variation because of the small thickness. There is hardly any variation in that, right? We will continue this in the next class. If you have any questions, you can ask now.